Hey, good morning, everyone. Thank you for coming to our workshop today. Before we start, if you have any questions, just throw your hand up. It'll be pretty relaxed, so yeah. Let's just look into the workshop overview. Introduction, that's us right now. We're going to go into Xatu Genesis, see sort of how it happened, why it happened, and then we'll look into the datasets that have emerged since. We'll then progress into how we're using the data, how others are using the data. Leo over here will then present, he's from the Mega Labs team. He'll present the big blocks test that happened last year. And then we'll have a live tutorial from Toni. He'll go through how he uses Xatu to run his analysis. Sweet. So a little intro on who we are. I'm Sam. That's Andrew. He's hiding. We've both been doing DevOps on the PandaOps team for the last few years. And we both have a deep appreciation for things like Ethereum and observability. As for our team, ETH PandaOps, we started out in 2021, being thrown straight into the deep end with the merge. We're embedded in the F and do DevOps for the protocol. And we post blogs semi-frequently on our website. We try to keep them really high signal. They're the best way to keep up to date with us. Scan the QR code, and it'll jump you straight there. Our team has a pretty wide range of projects cooking at all times. You've probably come across a couple of them. For example, if you've ever run a node, you've probably checkpoint synced from an endpoint that was running checkpoint Z. You may have also seen Parry and Barnabas whipping core devs in the core dev calls. Yeah, there's a lot of stuff going on. So let's move on to the workshop. To set the scene, it's late 2022 and the merge has just happened. We've switched from proof of work to proof of stake, but in doing so, our consensus mechanism has become a lot more sensitive to time. Suddenly, the when of things happening has become a lot more important. And this data at a global and network level doesn't really exist. It's easy to check that a block was seen, but it's much harder to see when that block was actually seen in Sydney compared to Berlin, for example. And now that we're clear from the merge, researchers start hacking away. They want to upgrade the beacon chain, but yeah, they need this timing data to validate their ideas. And they start capturing it themselves. Varying scales, different implementations, it's hard to expose, it's hard to validate. There's a bit of potential errors in there. So we started to brainstorm ideas on how to solve our problems. We needed to somehow integrate with existing beacon node implementations, as neither of us were really too keen to implement a full beacon node. As DevOps engineers, we'd usually just implement a few Prometheus metrics, put the feed up, and call it a day. But millisecond level precision is pretty important, so that rules out Prometheus metrics. Log aggregation was also another option, but it's definitely a moving target. These things change all the time. It's not really something that the client devs really pay too much attention to, and we'd also just have to turn on debug level logging. We'd be throwing the kitchen sink at our log aggregation pipeline, and it would potentially be an unreliable result anyway. So that rules out logs. So we started to look at other options. Turns out that the Beacon API has this thing called the event stream. You can subscribe to it, and when the Beacon node sees things or does things, it will emit an event. So blocks, attestations, voluntary exits, everything. It was all there. The beautiful thing is that the Beacon node implementation all supported this endpoint in a standardized fashion. So what we landed on was Xatu. We used Go, gRPC, and we thought that it would be responsible for just collecting Ethereum timing data. It definitely wasn't going to be trying to store or query that data, but the plan was to derive events and ship them somewhere else. To do this, we initially created two modules. Xatu server would create events from other modules, would collect events from other modules and send them somewhere else. And Xatu Sentry was our first module. It would run as a sidecar next to every beacon node, subscribe to events, and send them off to Xatu server. We wanted to make sure that all of the events followed the same structure so that it was much easier to add new events into the future. And also, really importantly, since this is like a distributed system, we wanted to make it clear how much you could trust the data. So data coming from a client is not necessarily trusted, but if it's been derived by Xatu's server, something that we control, maybe you can trust it a bit more. This example event is for one of our Xatu Sentry nodes running on mainnet, subscribing to a beacon node, and a new block has just come in. I've redacted a couple of the fields, but yeah, that's the general idea. That's all great, but we still hadn't really solved where to send the data. And it turns out it was a lot of data. Fortunately for us, ClickHouse exists, and it is goated. It allows us to store events at a scale that we didn't really think was possible. In July, we hit 4 commas of attestations in our ClickHouse cluster with just 14 terabytes of disk usage, which is just ridiculous. Given that those attestations, we don't keep the signature because we're getting it past the trusted point. But yeah, still, it's crazy. All right, datasets. I'll hand over to Andrew.
Datasets. So we just started with Beacon API events, and sort of over the last 2 years, we've been trying to collect it all the data, as the project name suggests. There's some overlap between the datasets. For example, the Beacon API event stream and the libp2p datasets sort of collect events at the head of the chain as they're happening. Whereas canonical sort of Beacon events and execution events is sort of the finalized data which can be referenced from other data sets. So there's a lot of sort of cross sort of queries that happen. There's also, so the module SAM talk about like the Sentry and the libp2p Sentry. We run lots of them. We collect a lot of the same event from a lot of different regions around the world. And that sort of gives us propagation times, timing data, regional data, sort of what's happening in Europe, what's happening in US, what's happening in Australia. Sort of allows you to sort of differentiate sort of what's happening around the world. We also collect MEV relay data, sort of bids, proposer payloads. We have a sort of discovery module that sort of crawls the execution layer, captures mempool from different regions around the world, and we also capture canonical execution sort of data. we like to use open source projects, a couple here. So Hermes by ProbeLab is a sort of libp2p sentry, I guess you could call it, that you run. Connects directly to the libp2p sort of gossip sub network, and you can sort of capture that data right off the network. So it's pretty good. And we also use Cryo by Paradigm. It allows us to get the sort of canonical execution data. Pretty good. We just sort of backfilled all the way to Genesis, basically, and made that public a couple of weeks ago, which is a lot of data. Also, check out Storm from Paradigm talk later today on data sovereignty. Should be good. Also, check out ProbeLab's talk yesterday on how they do a lot of work around the peer-to-peer network. It's pretty interesting. Yeah, so we were collecting a lot of data for researchers. We didn't really know what to do with it. There was sort of internal EF researchers and a few researchers outside. So we decided to open source it and sort of put it in Parquet files and make it available to everyone. You can read more there. There's a bit more sort of docs on how to sort of access and read it, but sort of every, some tables will be like per day or per hour, depending on how big they are. So you can grab, for example, block events for that date, and you'll get the sort of raw data in Parquet file. So if you want to do analysis, it's pretty easy to get started. Yeah, a couple of months ago we allowed, so we have a lot of sentries around the world capturing Beacon API event stream data. It's quite costly because you have to run obviously a beacon node and attach a sentry. We sort of allowed the community, if they want to run the sentry next to their beacon node. You can opt into sort of what sort of level of geo-IP data you want to send us, whether it's city, country, continent, or none at all. So it's up to you guys, but if you want to sort of contribute, we're open to that as well. It's just good to get data from a wide variety of regions and setups, and it just helps research as well. And all that data we anonymize, so you can, no one can sort of track what beacon node you're running, anything like that, but we also publish that data, so you can also check it out yourself as well. All right, using the data. This one's pretty interesting. We use SIGP's Block Scout block print tool, which you can check out there. It basically uses machine learning to try and assign a consensus layer client to a validator index. We then use that data, because we've got all this data, we know who's supposed to be attesting, we know who's not attesting, we can then link that to client data, and it gives us pretty quick response time to figure out if there's an issue with a particular consensus client implementation, because you'll see potentially thousands of validators offline for a certain client implementation. So this is really actually useful. We've got other sort of dashboards, Grafana dashboards we use for devnets, testnets, mainnet, around block timings and stuff like that we use internally. But yeah, there's a lot of monitoring goes on sort of about the network, about timing. Just gives us another view of the network. There's also ProbeLab, which I mentioned before. So they do some cool work. So they have a weekly report that uses Xatu data. It shows block arrival time. I think there's also the size of the block and the distribution there. Check it out. It's pretty cool. Yeah, they're doing great work. After 4844, we had a ESP data challenge, which was basically write a blog post about the blobs upgrade. There was definitely some cool blog posts there. I just picked out one here, which is pretty interesting. But yeah, in the future, there could also be more opportunities for data challenge. Just keep an eye out. Also, there's another one from Evan from, I'm going to butcher that, I don't know if it's Premev or Prime V, but he did a pre and post sort of analysis of 4844, which is pretty cool, using our data. Lastly, some randoms use our data on ETH research, which is cool. So yeah, that's basically it. Thanks for that. I'll pass it on to Leo to talk about his awesome work.
Thank you, Andrew. So good morning, everyone. Thank you for coming to this session. Yeah, I'm Leo from Mika Labs, and by the way, we have a booth on front of Classroom E in case you want to drop by and keep asking questions about what I'm going to present here or something else, the work that we do. So yes, I want to talk a little bit about this research that we did with the Xatu data. Just to put you in context, this happened last year in 2023. We have been working with the Ethereum Foundation researchers about data availability sampling. And one of the things that we wanted to know is how much time does it take to disseminate a huge block in the Ethereum network. So we were building a simulator that disseminates huge blocks over the network, and we managed to, after some months of work, to have some idea about how much time does it take to disseminate data of the network. But then we needed to somehow validate these results that we were getting with our simulator, and so we were, scratching our heads on how to do that. And one of the ideas was, okay, how about we pay a huge transaction into a huge block in the Ethereum network, and we, see how much that how much time does it take to propagate over the network. So we kind of artificially injected, and by we I mean the Ethereum Foundation, injected big blocks on the network, and then thanks to the Xatu, Sentry nodes and Xatu, we managed to see how much time does it take to propagate. Then a couple of weeks later, I was looking at the data, and we were recording the block sizes for the last kind of 6 months or something like that, and we noticed that there were plenty of big blocks in the network. And then at that moment, I contacted the EF researchers, so I was working with Danny Ryan and Dan Rudd at the time, and I say, hi, you guys are still injecting blocks? And they told me, no, that is over. And I said, well, I am seeing these huge blocks on the network. What is going on? And so this is when we kind of discovered that there is quite a significant number of big blocks that occur naturally, organically in the Ethereum network. And so this figure that you see here is an example of that. So this is 6 months, I think, from April to August 2023. And we are plotting all the blocks that are over 250 kilobytes in this distribution. So please notice that this is a logarithmic scale on the y-axis, right? And then you see that we go to up to over 2 megabytes of size for some blocks. Now, we also found quite weird to see blocks over 2 megabytes, because if you know how the gas system and the cold data works on the blocks, you know that usually you have 30,000 gas to pay, sorry, 30 million, and you have, and then if you want to store 1 byte of data, you have to pay 16 gas. And so if you make the computation, that says that the biggest block in the network should be only 1.8 megabytes. And so we look at that, but in fact, the reality is that if you pay for zeros, then that is for gas. So yes? This is pre-DNF, yeah. So this was last year in 2023. So the question for it was whether this is pre-DNF or after 4844. This was last year, so this is before that. And yeah, so then actually, in reality, you could actually construct a block that is up to 7 megabytes or so. And so because we had all these blocks, then we can actually have a lot of fun and try to analyze how these blocks propagate in the data. And that gives us a lot of information about how much we can increase the number of blobs in the future for data availability sampling and so on. So thanks to Xatu and the Sentry nodes that the DevOps guys deploy over the planet, as Andrew was mentioning, you can analyze how things behave in different regions of the world, right? And so we took this set of big blocks, and we try to analyze what is the distribution of arrival in different locations. So one of the things that you can try to analyze is, for example, okay, what is the difference of the blocks arriving between Amsterdam and, for example, Sydney? And you see this more or less like half of a second for this particular case. And you also see that most of the times the block arrives within 4 seconds, which is great. Otherwise, these things will not work because the slots are 12 seconds. So you need this data to arrive quite fast. That was one type of analysis that you could do. But then the other thing that we were actually really more interested is how blocks arrive according to their size. So we put the blocks in different bins, in different colors, from 0.2 megabytes to 2 megabytes, right? And then we analyze how much time does it take for those blocks, according to their size, to propagate over the network. And this is more or less the distribution that you see. So you see, for example, that there is between 200 kilobytes to 2 megabytes, there is almost like a 2 seconds difference right there for that difference of size in blocks, right? So that is quite interesting because then that gives us information about, okay, what is going to happen when we activate 4844, right, after the Devcon fork. So this was actually really great results because 2 megabytes is actually a lot. Right now we have maximum 6 blobs, which is about 700 something kilobytes. And so we say, okay, that's fine. If we already have 2 megabytes blocks that propagate over the network without any problem, and we didn't even notice it, that means that we can allow for 6 blobs to run over the network, and we should be okay. Okay? And then we deployed Devcon, and we noticed that, yeah, that actually works. And then this kind of data give us information also about how much further we can go in the future, right? Before we implement data sharding or PRDAS or whatever we want to call them. So this is why this kind of data is important for researchers, and this is what why this is important. And another thing that I want to show is, so we created this Xatu dashboard. You can access it on the QR code if you want. That give us real-time data on data that we get from Xatu. So we have a bunch of different things that I'm not gonna go into detail, but I just wanted to mention maybe just a couple of them, and then you can go and look at the details later. Or again, if you want, you can come at the booth and we can discuss about it. So things you can see here. So for example, this is a difference of how the number of blobs looked at the beginning. So this was during the first 3 months of after Devcon was deployed, and this is how it looks today. So at the time, you had like 56% of the blocks with 0 blobs, and today you have like 40%. So the blue color, the blue size here, has reduced significantly from the initial, the first months of Devcon up to today. So this is the last month, just like October. And you have seen that the other colors have increased in size on this pie chart, right? So this has changed. The number of blocks with six blobs keeps more or less constant. So in this case, I think it was 20%. Right now, we are 21%. So that one is more or less constant, but the other ones are increasing in size on this pie chart, while the number of blocks with 0 blobs is decreasing. Toni has also a very nice post that shows how this distribution changes over time, not only for the counts of blobs, but for many other things. So I also advise you to check on that one. And then you can also see in real time the propagation of blobs over the network, right? So you have all these events that Xatu is recording, and then you can plot all that for the last month, for example. You can plot all the blocks and all the blobs and see what is the latency of arrival for all the blobs in the network, right? Again, you can access this data on our dashboard, and we also have an API in case you want to play with the data as well. Another thing that you can do is try to look at how much blobs are used. So that means how much data is actually put inside. So when you have a blob and then at the end you have like 50 kilobytes of zeros, then we are assuming that that is not used, right? And so you can look at those details and see what is the usage of the blobs. And so this is how it looks from the last month. So I think they are in fairly good use of the blobs. So that's like almost 90% of the space is being used in the blobs. That was not the case some months ago. It was something around 60%, I think, some time ago. So this is also evolving, as rollups and layer 2s get more familiar with how to use blob data. This is changing. So again, if you're interested, please look at the dashboard. And another question that was interesting to analyze was how many miss blocks occur after some number of blobs, right? And this is important because if it takes too much time to propagate a block with six blobs, then what are the chances that the next one is going to be a miss? Because the block proposer was busy downloading blobs or whatever. And so this is something that we looked at. This was actually a question that was raised during the interop in Kenya and that we wanted to analyze. And so Xatu allows you to do this kind of analysis. And so this is, again, one of the pie charts that is shown in our dashboard in real time. And you can see that most of the blocks that were missed in the last month occur just after a block with 0 blobs, okay? And again, you have the distribution over here, but there is not such a strong correlation that you will believe that, okay, every time you see a block with 6 blobs, then the chances of missing the next one are very, very high. That's not what you see in this data. And again, there is a post by Toni on that, so also advise you to look at that. Maybe he will mention it later. Yeah, so I think that's more or less what I have today, and then we can move on to Toni. Thank you.
Can you switch to my computer? Perfect. Yeah, hi everyone. So my part will basically be about how I use Xatu for my daily analysis. And I want to focus especially on PyXatu, which is basically a library in Python. If you're familiar with web3.py, for example, this is basically what I try to achieve here. Allowing users to have a very high level, very easy access to the Xatu database, and then coming up with some functions, abstracting the complexity of Xatu. Although Xatu is not very complex, but of course you can always make it simpler by wrapping in within a Python library. And so let me show you the GitHub. So you can find my GitHub. There is a Xatu library, and you can install it very easily by simply doing pip install Xatu. And then you have to run xatu.setup, which will copy a configuration file into your home directory. There you have to put in your credentials, and then you're ready to go. So if you need credentials for Xatu, I would just say reach out to the Eve PandaOps team. They are very happy to provide you those. And yeah, so as soon as you have the credentials in your home directory, you can already start by doing something like this. We basically, okay, now I have to kind of, pardon? Dimming the lights, is that possible? Can we dim the light if that's possible? Okay, let me see how do you want to hold it? Okay. Okay, let's see. Oh, it's taped. It's taped to the table, okay. Then, very nice. Maybe you want to use that chair. Okay. Okay. So how I would start, it's basically importing the Xatu database, import Xatu. Then I would create the object that basically inherits all the functions, which is Xatu. Sorry. Right. And then you already see, okay, I'm now connected to this endpoint, and I will then call this endpoint. So in the background, it's actually using SQL queries, but the Python library should allow you to make that as simple as possible. And the first use case that I thought would be maybe appropriate for having a quick demo is, what if we want to know what are the missed slots over time? So first thing I would do is I would have to find the right function. Everything is documented in the GitHub, but basically it's xatu.getMissedSlots. Right. And of course, I don't know which columns are actually behind this data set. So there's a data set called beacon slots or something similar. And in order to know which slot was actually missed, the simplest thing to do is we query all slots, and then we check which slot doesn't have an execution payload, right? Because if there is no execution payload, then this means basically there is no, nothing from the EL in that block, which means either the block was reorged or the block was missed. So what I would do is I would first get the docs from this specific function. So I would just check, okay, I need the get missed slot. I copy it, paste it, and then I can see all the different columns I can get from this data set that is behind the get missed slot function. For example, I'm now interested in actually only one thing. I only want the slot number, right? I don't need anything of any other column. I basically only want to know which slot number was missed. So the query would then look like the following. I would have xatu.getMissedSlots. First, I would specify the slot range that I want to query, which is done like this. Let's say 9 million to 10 million. And the second thing is the columns I want. And this looks like this. And now let's see if this works. Wonderful. So what we get here is basically now a Python set with all the slots that have been missed within slot 9 million and 10 million. And then I can continue by putting it into a pandas data frame. Let's do that very quickly. Oh, I haven't imported pandas yet. Okay. Let's see. df pandas, that would be like missed slots. Oh, I called it df. And then I think I need to specify the column here. Let's see if that works already. Looks good. Okay, that's nice. Now I have everything in the pandas data frame. And the next thing I will do is I want to map the slot number to the actual date, right? This is, yeah, please. This is all mainnet, yeah. So, yeah, I could mention that. When you query for this, sorry, it's actually here. You can also always specify additional parameters. I've skipped it now for simplicity, but basically you could say I only want it for a specific testnet. You could say Sepolia, Holeshki, but per default it's always mainnet. Because this is also very important. If you query Xatu, you always have to make sure that you're not mixing different nets up with each other, right? Because suddenly you get very strange things, I can tell you, where you're like, okay, is that actually is mainnet broken? But then you find out, okay, it's actually a testnet. But thanks for the question. Okay, so the next thing I want to do is basically add a date column. And there you can do the following. So I will use Python's Lambda function. That's very handy for use cases like that. And then there is a Xatu helper function. Let's see how it is called. Get slot date time, I guess. Yeah, let's use this one. And I would basically throw in the slot number, because every slot, you know, we have 12 seconds, so knowing the genesis time, we can exactly tell at which time a slot appeared. Let's see if that works. Wonderful. And now we are already quite far. So we have the date, the slot, and the last thing we need to do is then to group by the date. Let me quickly check. Okay. Let me see. Get slot. Okay, there's another helper function that will be simpler, slot today. Okay. Actually, let me use another helper function, because now I got very precise timing with seconds and everything. But in order to visualize this missed slots over time, we don't need the minutes, the hour, and everything. We basically want to have it grouped by day. So there is also slot today, right? And there I would do the same. Right, that's already a little better. And now I want to group that whole thing. Let's see. Group by. I want to group by date. I want to sum up the slots. Basically, I want to count them actually, because otherwise I would just add the slot numbers and then reset index. This is basically all some pandas stuff to get a nice data frame in the end. Index, and in the end we can sort it by date. Right, let's see if that works. Perfect. And then to make it 100% realistic, I show you exactly how the workflow works. You can already see ChatGPT is ready. I would basically do something like, give me, I like the library Plotly a lot, Plotly express chart visualizing my missed slots over the days. Paste in my data that I have, and then I had quite good experience with ChatGPT, so ChatGPT is really good at quickly creating those charts. So first, let's copy the whole thing. So I don't need this sample data that ChatGPT gave me, but I can see it put it into a df variable, so I would do something like df is my group df. And then let's see if that works already. Perfect, right? So this is actually a very simple example how you get to the missed slots. I don't know how much time it now took, like 5 minutes, 10 minutes, but it's a very realistic workflow. So this is how it looks like when I do many of my analysis. Of course, it gets a little more complex, especially if we want to go a little deeper. But for the missed slots, that's actually already it. The next thing we could do is maybe I should ask, is there a validator in this room? Or someone who has a favorite validator? Validator number 1. Okay, let's do Okay, yeah, and they are not yet withdrawn? Okay, let's see. Because one very interesting thing that you will not get anywhere else, but you get at the Xatu database, is you can check when your blocks are seen in the network. So you can check, okay, my validator proposed a block, and I want to know when did this block arrive in Europe, when did it arrive in the US, Australia, and so on. And this is very interesting, especially if you want to check who is playing timing games, are your blocks late? For example, if you build your blocks locally, you don't use MevBoost, then this is in particular interest of you, because you might want to know, okay, is my block out there at the network in 1 second into the slot or 3 seconds into the slot, right? Because if your block is very late, then you might want to consider using either MevBoost or, yeah, looking for better peers, and just to make sure that you will not be reorged. Okay, I see validator number 0 is active. Let's do it with validator number 0. So there is a function called xatu.getBlockEvent. Lock event, that's the one. I will just do the same slot range again, which was, where do I have it? I got it here. Let's do 9 million to 10 million. Okay, now we have to hope that this validator had a slot in this range, otherwise we'll just deviate to another one.
He proposed in August something. He proposed a block in August, yeah.
Okay, then we should find something. First, I do the get docs again, because this is always handy to see what Xatu is actually offering here. It's actually .get docs, and then I paste in the function name. Okay, what I need now is the event datetime. So Xatu, there are many different nodes all around the world, different clients, everything, and I want to know when are blocks seen by those different clients. And the block and the time seen is here the event datetime, because it means when was this event recorded, and because the events are recorded in real time as soon as they are seen, we should be able to use this event datetime. Then let's see what else we might need. Columns is equal to event datetime. We also need the slot, I guess, and we might need we also need the proposer ID, right? We want to know the proposer, which validator ID did the proposer actually have. But you can see this is, I think, not included in this data set. So we might need another query for the proposer, which tells us which proposer was supposed to propose in which slot. Get proposer, same range. And again, that's how it works. We go into the docs again, quickly check what is there. There is a slot and there's a proposer validator index. And I would then query those two. Slot plus proposer validator index. And then I should get a pandas data frame that shows me the slot and the proposer index. Now we can go on and merge those two data sets. So here we had the block event, which looked like a slot and the event datetime. Okay, I should have not run it again. Okay, looks good. Perfect, and then we can do something like pd.merge, proposer. We merge left, and we merge on the slot number. Left on slot. And then right on slot. Looks good. Right, and then we are already getting very close, right? Now we have the slot number, the proposer that proposed a block or was supposed to propose a block in that slot, and the event datetime when the block was seen. Could you come in? The next thing we would need to do is basically group another time because, for example, if you want to know when it was first seen, right, this is very interesting because, for example, if you want to know if someone is playing timing games, you want to know the first time the block was seen in the network. Usually that's in second like 1 in the slot, but if you play timing games, then it's like at second 3 in the slot. And what we can do here is basically group the whole thing. We group by slot and I think it works like this. We group by slot and propose a validator index. And then we take the minimum of the event datetime. Oh, damn. Okay. Okay, let me quickly check. Let me make sure that I didn't forget anything here. Yeah, it looks good. The maximum would be very different because sometimes a node sees a block, let's say, 20 seconds after it was actually proposed, right? For example, if the node is slightly behind or something, so you will find sometimes numbers that are much higher. For example, let's say the, I don't know, Nimbus-Geth combination in Australia had some problems right at that time. Then you might see numbers that are way too high, but usually all those nodes should agree on, yeah, some rough number. And I'm here interested in the first time we saw a block because this tells us with a very high likelihood that this is the time when the block was proposed. The block was actually proposed a little earlier, but usually this should be a quite good approximation. Okay, let me check because I just see I should have done reset index, set index. Let's do in place true. Okay, now maybe there is no in place. Let me try it like this. Ah, okay, that's fine. And now one very interesting thing is you've all seen on Dune dashboards, on my dashboards, we always use those validator labels, right? And it's super hard because you need those different heuristics to create those labels. But you can also use Xatu in the future. You can access it under xatu.validators and then .mapping. And what this gives you is basically the validator ID, public key, the deposit address, and all the labels that you see on Dune dashboards or on my dashboards about all those validators. So what we could do now is let's first check. Let's just merge it to our data set, what we have so far, which is the same again. Merge, df, we have the labels. We merge on the validator ID. So left, then we do left on. Okay, the left-hand side, it was called propose a validator index. And on the right side, it was called validator ID. Right. Okay, this looks good. Now we have all that information in our data frame. And what we can do now is we can already start looking for what is our target validator doing, validator with the ID 0. Oh. Okay, we want validator ID is equal to 0. Oh, there was no block. Let's try 1. Okay, validator ID 1 had a block in that time. So for example, we can see the time when it was seen, all the other information that we need. And finally, what we can do is there's another helper function for you that is telling you at which time in the slot the block was seen. So seconds in slot. And then we do df.apply. So I apply a function over the whole row. And then lambda x. And then I have to do Xatu helper. Helpers. And then I will do get time and slot. Okay. get the time in the slot. And what this function wants is basically the slot number and the actual time it was seen in the slot. So the slot number, we got it in the slot. And then the event date time. Okay, actually I forgot one important thing here. I just see that I should have converted this datetime into an actual Unix timestamp, but this is very easy. We do it like event datetime is equal to event datetime. And then you can do something like, Pandas has a function that makes sure that your field is actually a date format. So datetime, we can say UTC is true because all the times you find in Xatu are UTC. UTC is true, right? And then we can do something like as type, which means we convert from datetime to integer. Integer. And this now gives us milliseconds. We want seconds, which means we do something like 10 to the power of 6. This should be good enough. Let's quickly check if our dataset looks like expected. The event datetime, we now have the datetime in Unix timestamp. And the final thing we do is exactly this here. We continue with x.event datetime. Right, let me quickly check I didn't forget anything. Looks good. Okay, this is everyone who is familiar with pandas knows why I do certain things. For example, apply one because we now put in the whole row and not only one cell. And let's see if that works. Okay, this is kind of expected. Let's see where the bug is. Oh, it's access one and not apply. Yeah. Right. And what this does is basically we tell him the slot, we tell him the exact time we recorded the event, and using that information you can then tell at which second in the slot was the event actually seen. And now we have all the information we need. For example, what we can do is, let's actually do something like group by. We group by label, and then we do something like seconds in slot. We take let's do the median, and we reset index. Okay, let me quickly check. I think median without the brackets. No. Group by label, seconds in slot. Okay, there's a typo, huh? Oh, I still called it. I called it event datetime, right? No, I didn't do the seconds in slot yet, right? This one? The S. Oh, thank you, thank you. So this should work, perfect. And then we can do median. Right, and then we get the median time when every validator slot is seen. You can see we've got a lot of, looks like some solo stakers, but then we can also check like, okay, we all know that P2P, Kieln, there are some entities playing timing games, right? So what we could do is we do something like this, label equals, let's do Kieln. So for Kieln, the median time when the block is seen is 2.93. And then we can do the same. Let's see, for example, okay, no block in that time. Wait. Then you can see, okay, that's kind of the honest behavior. If you push your blocks out without playing timing games, your block should be seen within the first second of a slot. Whereas if you play timing games, you're at 2.9 seconds. And yeah, this is exactly how I did, for example, analysis on timing games. If you want more information, you can check out my ETH Research profile. I did many posts recently with especially pushing for a blob increase in Pectra, analyzing big blobs, analyzing reorgs. And yeah, if you have any more questions or interested in your own validator into another pool, just let me know and we can look it up. Thank you.
Any other questions? Sweet. Thanks for coming.